All right, I'm going to show you some details about the request response pattern in processes. So on my left here, I have a node running. I just started it up. It's running live on the Sepolia testnet. And on my right, I just have a terminal window open inside of a project that I've been working on. So I can see my project folder here, and I can run Kit, which is the development toolkit, in order to first build this project and then start it on this node. So I can just do that with Kit BS, which stands for build and start. So we compile two WASM processes in the package, and then we install it on the node. Now, we're going to look at this trace and see some things going on between process 1 and process 2. And after this finishes, we can look at the code that's actually doing this. So that's the end. And you can see here we've got two processes starting. We've got process 1 receiving some things, printing some things, and then we have some metrics coming out. Okay, next we're going to look at some code that produced the prints you just saw. So here we have two processes. Both of them are comprised entirely of a single library file. Here's process 1. Over here's process 2. So let's look at process 1 first, and then we'll bounce between the two because we're doing requests and responses. So we've got some boilerplate and some imports up here. And then we get into the init function of our process, which every function has, or every process has. So you see the start print here. We generate an address, which corresponds to process 2, which is running in the same package, but is named P2 instead of P1. First thing we do is fire off a request. This is just about the simplest request you can perform. We set the address that it's to. We set the body as just some bytes, and then we send it. And we can unwrap it here because we know that we've set a target and a body that are valid. So this happens without any fanfare. The next thing we do here is send and await a response. So this is a slightly more complex pattern, but still very simple, where we fire a request and then we send and await it. So we immediately receive a potential response here. So this returns a result, which can either be a response message or a send error, which contains a timeout. So what you see in the comment here is that P2 is programmed to wait 2 seconds. And since we're only waiting 1 second, we're setting a timeout of 1 second. This is going to fail. So we get this maybe message, and we check is okay. And if you recall, in the terminal, we saw that this printed false. So it timed out. Let's look at process 2. Process 2 is also very simple, but it has a handle message function here. Let's scroll down to the init function. In the init function, all we do is print start, and then we repeatedly call handle message until we get an error, in which case we would break. So let's look at handle message now. Handle message is a very simple switch statement that first calls await message, which does exactly what it says. And then we match on that message body. We throw an error if we get a send error here. So if we look at the request here, we said, please respond. We're matching very simply on the body bytes here. You can see, please respond. We're programmed to sleep for 2 seconds and then respond. Now, you'll see some other things here we'll get into, but if we're looking at this response, this fails because we only waited 1 second. Down here, we wait 5 seconds, and if you recall on the terminal, this printed true. So we see, okay, P2 did in fact respond to us. So that's a very simple request response pattern that you can build and send a request, block in place, and get the response out. Next, we're going to look at what blobs are. So blobs are arbitrary data payloads that you can either pull into your process or not pull into your process, unlike the body, which is a byte payload that is always pulled in when you receive a new message. So here we've got a body that says, please respond. We've got blob bytes, this simple byte vector, and we send an awaited response. After awaiting and receiving that response, which note we don't actually care about, we call getBlob to, again, optionally access that lazy load payload. So the goal here is to assert that the response does not have a blob. So if we go back to P2 here, we're matching on this please respond. You see we send a simple response, there's no blob. This assertion thus is successful. Next, we want to receive a response with a blob. So we send the same request, but this time we say, please respond with blob. We attach a blob, and then we await the response and assert that that response did in fact have this same vector that we attached. Now, we could have gotten a different blob payload from P2, but if we look at the logic of P2, we see that P2 responds without actually creating that vector. All it does is mark inherit as true. So what's going on here is that P2 is receiving the request with the attached bytes payload in the blob. But instead of ingesting that into the WASM process and thus incurring a small performance cost, we simply say, hey, respond, and we're going to mark this message as inheriting the blob and context of the message that we just received. So we inherit the blob from the request, and so we echo it right back at P1. So let's see some actual metrics to prove that we are in fact saving some performance by doing this. If you recall, in the terminal, we had a print here that said 100 requests with 100 megabyte blob took about 5 seconds, whereas this next one with 100 requests and 100 megabyte blob on each request only took about 2.5 seconds. So we save an enormous amount of time actually by not ingesting the blob. Both of these processes are running on the same node. So a 50% saving indicates that basically the fixed cost of generating and sending this blob in P1 is probably around 2.5 seconds. The fixed cost of ingesting all those blobs in P2 is probably about 2.5. So if we see a 50% performance increase between this first thing where we grab the blob and the second thing where we don't, we're looking at basically it costs nothing to ingest this message without that blob, which makes sense because 100 megabytes is a lot to copy across the WASM barrier. So we do a simple for loop here. We say, okay, let's create 100 requests with this blob vector that's just 100 megabytes sort of zeros, and we send and await the response. We wait 1 second. Now, we do get these responses because we're actually unwrapping. We're panicking if we don't get an okay response here. And then we see, okay, yeah, this whole process of sending and receiving the responses took this amount of time. In P2, we're branching on this and we're saying, please grab this blob. P2 grabs the blob, then responds, inherit true. It's sending the blob back, but it's also grabbing it. And this is what's creating that performance cost. If we look at please ignore this blob, where in P1 we've got pretty much the same exact logic here, except we changed the body, the instruction in the body. We respond, we inherit true, so P1 can still go grab that blob it just sent us, but look, we don't actually grab it like we do in the above switch option. So big performance savings here, and this enables all kinds of middleware to potentially interact with protocols that are sending large amounts of data without incurring any cost for passing that data. Potentially, lots and lots of times between processes before that data blob arrives at its final destination. So that's the bulk of this. We've got one more pattern on display here where we send a request, we wait for its response, but we let the other process perform different actions before it responds to us. So I'll just walk through the logic here and then explain it. So in process one, we send a request. We expect a response, but we don't wait for it in place. Instead, we loop and await message. We wait for this response we wait for a request from process two, and we respond to them. Then, after giving that response, we wait and look for the response we're going to get from this first request. So we send a request, we handle a request and give a response, and then we wait for our response from our original request. Over in P2, this looks like this switch statement right here. We receive the request, we send a request of our own back to P1, separate from this original request that we're handling. We await its response, and then we take the body from that response and we send it in our response. Now, this is happening between P1 and P2, but this could be happening between many, many processes. Instead of calling back to P1 here, P2 could call out to P3, P4, P5, whatever, any process, and do some work, and then finally respond to that original request that it's handling. And this is because when we generate requests and responses, they operate within a context that's basically calculated by the kernel for you to determine where to route responses that you create. When we receive this request, we know that we have an outstanding request. We can fire a request of our own and await its response without losing that context. So ultimately, P1 receives this response that it expects, even though other things happen in the interim. And that takes us to the end of these two processes. I hope this was informative in knowing how requests and responses work